At 2:17 a.m. on July 19, 2024, Tom Novak stood at the control panel of a Valley Center pivot irrigation system, watching pressure gauges drop on Section 14 of his farm near Ogallala, Nebraska. 51 years old, third-generation irrigator, 4,800 acres under management. The digital display showed well pump flow rate declining, 950 gallons per minute, then 920, then 890. Normal rate, 1,000 GPM. His corn was at critical growth stage, tasseling and silking, when water stress cut yields by 8 bushels per acre per day of deficit. The Ogallala Aquifer beneath his feet had dropped 127 feet since his grandfather drilled the first well in 1962. Standard practice said, shut down the system, call the pump technician in the morning, accept the loss. His yield monitor data showed this section averaging 218 bushels per acre, his best ground. At current corn prices of $4.35 per bushel, every day of lost irrigation cost him $17,000. Weather forecast showed 98-degree heat for the next week. Novak grabbed his tools and headed to the well house. Nebraska's irrigated corn system operates at a scale visible from space. 9 million acres. That's 14,062 square miles of cropland sustained almost entirely by groundwater, pumped through 50,000 center pivot irrigation systems, each creating perfect circles, 125 to 160 acres in size. The geometric patterns, green circles against brown dry land, mark one of agriculture's most dramatic transformations. Every summer, approximately 1.7 billion bushels of corn, worth $7.4 billion, depends on roughly 5 million acre-feet of water lifted from the Ogallala Aquifer at depths averaging 200 feet. This water feeds America's largest concentration of cattle feedlots, 2.4 million head on feed at any moment, and supplies 25% of the nation's ethanol production capacity. The system functions through precision technology. GPS, guided combines harvesting in circular patterns matching irrigation geometry, variable rate fertilizer application adjusted to square meter resolution, real-time yield monitoring, creating data maps showing productivity invisible to human eyes. This is industrial agriculture optimized for maximum efficiency. It's also agriculture dependent on groundwater extraction rates that exceed natural recharge by 36 to 1. Thus, Tom Novak learned irrigation from his father, who learned from his grandfather, who switched from dryland wheat to irrigated corn in 1962 when affordable turbine pumps made groundwater accessible. His grandfather's first system was side-roll irrigation. Aluminum pipes on wheels moved by hand every 12 hours. Labor-intensive. Revolutionary. Corn yields jumped from 45 bushels per acre dryland to 110 bushels irrigated. By 1978, his father had converted to center pivots. Automated systems rotating around central wells, eliminating hand labor. Yields climbed to 160 bushels. Novak took over in 1998, installing GPS guidance, variable rate nozzles, soil moisture sensors. Current yields, 215 bushels per acre average. The technology improved continuously. The aquifer declined relentlessly. Every year, the water table dropped another 1.8 feet. Every year, wells needed to go deeper, when the tension between productivity and sustainability defined everything. The well house sat 400 yards from the pivot point. Novak arrived at 2:35 a.m., opened the door, heard the problem immediately. The submersible pump 220 feet below ground was cavitating, sucking air mixed with water. The aquifer level had dropped below the pump intake. This well, drilled in 1985 to 280 feet, had been reliable for 39 years. Water table at installation, 160 feet. Current level, 235 feet. Although the pump intake sat at 230 feet, it had finally run dry. Novak shut down the system. The silence felt like failure. This section, 480 acres of his best soil, would get no water until he could lower the pump 50 feet deeper or drill a new well. Lowering meant pulling 280 feet of drop pipe and electrical cable. 3 days of specialized work costing $18,000. Drilling a new well to 320 feet meant $65,000 and 2 weeks. Meanwhile, corn would stress. Yields would collapse. He'd invested $2,280 per acre in this crop. Seed, fertilizer, chemicals, fuel. At 218 bushels per acre and $4.35 per bushel, gross revenue ran $948 per acre. Operating costs consumed $720. That left $228 profit per acre. 7 days of water stress would cut yields by 56 bushels, $243 per acre in lost revenue. He'd go from profitable to losing money. He called the well service company at 6 a.m. They could start in 4 days. Unacceptable. He called 2 more companies. Same answer. Our peak irrigation season, everyone booked. He made a decision. Hire an emergency crew from Kansas at premium rates. $28,000 for 3-day service. Nearly $6,000 per acre to save the crop. The math barely worked, but total crop failure meant catastrophic losses. The economics of Nebraska irrigated corn create dependencies farmers can't escape. At $4.35 per bushel, every acre yielding 215 bushels generates $935 in gross revenue. Seed costs $140 per acre for hybrid genetics, optimized for irrigation. Our fertilizer adds $195 per acre. Nitrogen, phosphorus, potassium, sulfur applied through fertigation systems. Chemicals, herbicides, insecticides, fungicides add $78. Irrigation costs run $85 per acre. Electricity to pump a water, system maintenance, equipment depreciation, fuel and machinery, $112. Crop insurance, $42. Land costs, $220 per acre, whether rent or opportunity cost. Total operating costs, $872 per acre against $935 revenue. No, that leaves $63 profit per acre before equipment depreciation and loan payments. Across 4,800 acres, Novak generates $4.48 million in gross revenue and maybe $300 to $2,400 in operating profit. After depreciation and debt service. Actual net income around $165,000. For managing $12 million in equipment and land assets. The return on investment is 1.4%. The system works only because no alternative exists. The emergency well crew arrived July 22nd at 6 a.m. Were 3 men with specialized equipment designed to pull submersible pumps. Novak watched. Disconnect electrical panel, unbolt pump housing, attach winch cable, begin the slow pull. 20 feet of pipe at a time. By 4 p.m., the pump emerged, 75 horsepower, coated in mineral deposits. The crew recommended replacement. New pump, $8,400. Novak agreed. What choice existed? They lowered the new pump to 270 feet, 10 feet above current aquifer level with room for further decline, reconnected components. Started the system at 6:45 p.m. July 23rd. Water flowed. The pivot began rotating. Novak walked to the section center and watched irrigation nozzles spray in perfect patterns. The corn looked stressed, leaves curling, growth stunted. But it would survive. Yields would drop maybe 20 bushels from peak potential, costing roughly $42,000. Add the $28,000 repair cost. Total damage. $70,000 for 3 days of downtime, $145 per acre. Twice his profit margin on this section. One emergency wiped out profit from 2 sections. His phone buzzed. Text from his daughter Rachel, who managed precision agriculture systems from Lincoln. She'd been monitoring soil moisture data remotely. Glad you got it fixed. But Dad, we need to talk about the aquifer. I ran projections. At current depletion rates, we'll hit critical levels on 6 more wells within 3 years. Novak knew the numbers. Nebraska's Ogallala Aquifer, the massive underground reservoir stretching from South Dakota to Texas, was being drained at rates exceeding recharge by 36 to 1. Western counties where Novak farmed had already lost 30 to 50% of total water. Some areas had maybe 40 years left at current usage, maybe 60 with strict conservation. His grandchildren would face impossible choices: farm without irrigation or abandon farming entirely. Then the center pivot system covering Section 14 represented peak agricultural engineering. The machine stretched 1,320 feet from central pivot to outer tower. A quarter-mile of galvanized steel pipe supported by wheeled towers spaced 160 feet apart. Each tower contained electric motors and control systems, keeping the structure moving in synchronized rotation. The system completed 1 revolution in 72 hours, applying 1.2 inches of water per cycle. GPS guidance maintained circular perfection. Variable rate nozzles controlled by software linked to soil sensors applied different amounts to different zones based on real-time data. The technology was extraordinary. The physics were brutal. Pump 5 million acre-feet annually from an aquifer recharged at 500,000 acre-feet. The deficit was 4.5 million acre-feet every year. Nebraska irrigators were mining water, not farming sustainably. Novak's operation used approximately 8,200 acre-feet annually across 4,800 irrigated acres. That's 2.67 billion gallons. Electricity to pump that volume cost $68,000 annually. His wells operated 2,400 hours during irrigation season, 100 days at 24 hours daily. The pumps drew 1.2 megawatts combined, enough to power 900 homes. Without irrigation, his land would revert to dryland corn at maybe 80 bushels per acre. A 63% yield reduction, making farming financially impossible at current land values and input costs. Rachel arrived July 25th to discuss long-term strategy. She brought data: aquifer decline rates, pumping costs over time, yield response to deficit irrigation, economic models under various scenarios. Her generation approached farming as systems to optimize, not traditions to preserve. Dad, we need deficit irrigation, strategic water stress at non-critical growth stages. We maintain 195 bushels per acre with 15% less water. That's 1,230 acre-feet saved annually. And give up 20 bushels per acre? That's $87 lost revenue. It's $87 per acre versus $145 per acre when wells fail unexpectedly. We're choosing between controlled decline and catastrophic failure. Novak understood her logic. Deficit irrigation, deliberately underwatering during vegetative stages, had research support. The yield penalty was real but manageable. More importantly, it extended aquifer productive life. But implementing it meant abandoning productivity maximization. For 30 years, he'd pushed for higher yields. Rachel asked him to accept lower yields deliberately. It felt like retreat. What's the endgame? Managed transition. farm at sustainable extraction rates, even if profits suffer short-term, or maximize production now and face harder transitions later. The conversation continued through dinner. His wife Linda listened without intervening. She'd heard these discussions for years. The conclusion was always the same. Continue farming efficiently. The hope for technology breakthroughs or policy changes. Avoid thinking too hard about the timeline. The alternative, admitting the entire irrigation economy was temporary, was too demoralizing. By harvest season, Section 14 had partially recovered. Novak ran the combine through in late October. Final results: 198 bushels per acre, 20 bushels below farm average. At 480 acres, that's 9,600 bushels lost. At $4.35 per bushel, $41,760 in lost revenue. Combined with $28,000 repair, $69,760 total cost. One equipment failure consumed profit from 3 sections. Tom Novak continued farming through 2027, implementing gradual conservation, efficient nozzles, better sensors, limited deficit irrigation. Water use dropped 11%, while yields fell only 6%. The aquifer continued declining at 1.8 feet annually. By 2028, 2 more wells needed deepening. Rachel developed comprehensive water management projecting sustainability through 2050, assuming strict conservation. The plan was sound, economically challenging, emotionally exhausting. In 2030, a major aquifer study confirmed what every irrigator knew. Current extraction was unsustainable, water levels were declining statewide, and without policy intervention, large areas would become unirrigatable within 40 to 50 years. The report prompted legislative debate about pumping regulations. The agricultural lobby fought restrictions. The debate continued without resolution. The pumps kept running. The water kept declining. Nebraska's 9 million acres of irrigated corn continue producing 1.7 billion bushels annually, feeding 2.4 million cattle, supplying 25% of ethanol production, supporting 47,000 farm families whose operations depend entirely on groundwater that will not last. The system functions through technological precision that has made Nebraska agriculture extraordinarily productive. It functions on borrowed time. These facts coexist without reconciling. Individual farmers manage operations as efficiently as possible while knowing the endpoint approaches. The technology improves. The aquifer declines. The circles keep rotating. If this story moved you, please like and subscribe. Your support helps us preserve these histories of American agriculture's transformation. Tell us in the comments where you're watching from and whether you understand the stakes of groundwater-dependent farming. Thank you for keeping their stories alive.